Hello dear listeners, we are starting our lesson about basics of random variables and especially about basics of discrete random variables. So what random variable is? Sometimes we can read that a random variable is variable which is random. Actually it is awful definition, it isn't definition at all. We'll provide better one. So let us focus on experiment with random outcomes. Outcomes of this experiment are random events. We say that event is random if we can't predict if it will occur or not. For example, when we toss a coin, we can't predict if we'll get a heads or a tails on the top side of the coin. These are random events. We describe our experiment with random outcomes with sample space omega the capital. We list all of elementary mutually exclusive events and gather them into the set. This set can consist of finite number of elementary events or infinite countable. But having a deal with sample space itself is rather inconvenient. So we'll provide a better mechanism. For each of the elementary events, we'll put in accordance the real number, specific real number. So if we toss a coin, we can say that we'll get 0 if heads will be on the top side, and we'll get 1 if on the top side will be tails. This way we define the random variable. So random variable is the function defined on the sample space, and this is a real function. Its values are real numbers. But is it enough to have a random variable? I mean, if this definition is enough for us. No, it isn't. Why not? Because we need a mechanism to be able to calculate probabilities of events connected with our defined random variable. So usually events in relation to the random variable have a look like this, like inequalities. So we need to be able to calculate probability that our random variable will take on value less than specific real number, some specific constant real number. So we say that xi, real function, defined on sample space omega the capital, is random variable if taking any real number a, we can calculate the probability of this event. Other words, the set of pre-images of xi which satisfy this inequality belong to sigma algebra F, and probability is exactly the real function defined on the sigma algebra F, which is constructed on the basis of sample space omega the capital. So that is definition of our random variable. Real function defined on omega the capital sample space, for which we can calculate probabilities of such events. Let us provide an example. Let us throw a plane cube with 6 sides and write down the sample space for this experiment. The sample space consists of 6 random events. Each random event corresponds to the number of dots on the top side of the plane cube. Let us define random variable xi, and our random variable xi will take on the number of dots on the top side of the plane cube. Very simple random variable. Let us provide an example. Let us throw a plane cube, 6-sided, and write down the sample space for this experiment. So our sample space here consists of 6 different elementary and mutually exclusive random events. And let us define the discrete random variable xi, which will take on the number of dots occurred on the top side of our plane cube. Here xi is discrete random variable. We say that random variable is discrete if it takes on isolated values. So random number of calls in the call center, or a random number of accidents on the plant, or a random number of customers in the store are random variables of these types. So here we have random variable which takes on isolated values 1, 2, 3, 4, 5, 6. These values we call possible values of random variable, because random variable xi takes on these values with non-zero probability. To define distribution law of discrete random variable, we list all of possible values in the first row of the table and list corresponding probabilities in the second row of the table. So here we have table distribution law of discrete random variable xi. But on the same sample space can be defined not only this random variable, but a lot of other random variables. For example, let us define random variable xi with a star. This random variable will take on value 0 if number of dots on the top side of the cube is not greater than 4, and will take on value 1 otherwise. So xi with a star will take on value 0 if one of these 4 random events will occur, and will take value 1 if one of these 2 random events will occur. Random events xi with a star will take on value 0, and xi with a star will take on value 1, are mutually exclusive, and the sum of them is a sure event. So from here we can see one important property of discrete random variables. The sum of values in the second row should be 1, as it is the probability of sure event, and because these random events are mutually exclusive. And another important property: random variable xi is a function. So to every pre-image it provides only one image. And if we'll try to define random variable xi with 2 stars, which will take on value 0 if the number of dots on the top side of the cube is even, and will take on value 1 if number of dots on the top side of the cube is divisible by 3, then will happen nothing good. We can't do this way, because in this case this random variable should take on the value 0 and 1 at the same time, when this random variable will occur. And this can't happen if we have a function. So to every image from omega the capital, C should provide only one image. But as we have seen, the image can correspond to several pre-images, like in this case. So it's enough for today. Thank you for listening. See you on the next lesson, and goodbye.